Welcome back to Algorithms and Uncertainty. Today we will be considering another problem of stochastic probing. What does this mean? We are given some boxes in which we will find prizes when we open them. We may open a couple of them, but then we may take home only a single of these prizes, so probably we will take home the highest prize. But the setting is now different from the Pandora's box setting, where the boxes had opening costs. This is now different because opening boxes, it doesn't cost anything, but we have the constraint that we may open at most k boxes. So let's formalize this. So we have n boxes, which we'll just number 1 through n, and xi, this is now the random prize inside box I. Xi is drawn from some distribution di independently. And these di, those are known in advance. But not necessarily identical. And what is now different from Pandora's box? We may open up to k boxes, and our reward will be simply take the maximum of all xi in boxes that we opened. So opened, this is just a subset of 1 through n. Those are the boxes that we open. And what else will we write down now? Let me already introduce some notation. F subscript I comma v, this is what we'll use as a notation to say this is the probability that xi takes the value vi. So for simplicity, we'll assume that those are discrete distributions. Just to keep our calculations simple, in general, actually, the approach that we are taking would also work for continuous distributions. Good. So modeling this as a Markov decision process is actually pretty easy. It's pretty straightforward. Once again, you would have an exponential number of states because you would have to keep track of which boxes you opened so far. And this is why this is actually a pretty difficult problem to solve. For Pandora's box, we had a pretty simple policy, which boxes to open in which order. But this is actually pretty much different for this problem, although it feels pretty much the same. The only difference is that we are only allowed to open k boxes rather than having a cost associated to open a box. Let's see what I mean by this. Let's see this in an example. We might have 3 boxes, and those look as follows. We'll have x1, for example, may contain a price of 20. So the first box contains a price of 24 with probability a half, and it is empty otherwise. So also with probability a half. We have a second box which contains a price of 30 with probability a third and is empty otherwise. And we have a third box which always contains a price of 12. So this is happening with probability 1. And I'm now giving you the constraint that you may open up to 2 boxes. So what does this look like? Well, we have now 3 boxes. This is our first box. We have a price of 24 inside it with probability half, otherwise it's empty. We have a second box which contains a price of 30 with probability a third, and a third box which always contains a price of 1. And you're allowed to open 2 of these 3 boxes. What do you do? Well, what you might now do is you might say, okay, I open the first and the second box, or I say I open the second and the third, or the first and the third. What's the best way of opening the boxes this way? Let's see this. So if we open boxes 1 and 2, what's the expected price? This will be equal to the expectation of the maximum of x1 and x2. So this will be a third times 30 plus 2/3 times a half times 24, which is 18. Why that? Because now with probability a third, we'll find the 30 in the first box, or with probability 2/3, it is empty. Then we open the second box. There we'll find a price of 24 with probability a half. And if you now do the math, you'll see, okay, this will be 18. You can open boxes 1 and 3 also. And then, what is it that you're getting? You're getting the expectation of the maximum of x1 and x3. So what you will now be getting is, with probability a half, you're taking home 24, and with probability a half, you're taking home 12, which is also 18. And let's open boxes 2 and 3. Now, what's the expectation of the maximum of x2 and x3? Well, this is now a third times 30 plus 2/3 times 12, and this is 18/2. Okay, so in this case, it apparently doesn't actually matter which pair of boxes we open. But then I hope you are a little smart and you say, oh, actually, do I have to commit in advance which of the 2 boxes I open? And what you might want to do is you might want to just take this box 1 and just look inside. Let's do this. And in this case, we find 24. Okay. Then there's certainly no point in opening this box, because all that we can find inside this box will be 12. So why should we open this box anymore? Then we can take the chance of opening the 30 box. But suppose now we did not find the 24 inside. Then we are suddenly in the case that we have no price so far, and we have to choose between 12 with probability 1 and 30 with probability a third. And how would you decide then? Well, then certainly you would take the 12, which gives you more than the 10 that you're getting out of the other box in expectation. So rather than being non-adaptive and fixing in advance which of the two boxes you'll open, it is a better policy to first open one box, see what's inside, and then to adapt your decision based on what you find inside. And let's see what this means here. A better adaptive policy is open box 1, and if it is empty, we open box 3, and if it is not empty, we'll open box 2. And what's the expected reward? Well, with probability a half, we are in the first case, so in this case, that the box is not empty. So then what will happen is that with probability a third, we're taking home 30, and with probability 2/3, we're taking home 24. Or with probability a half, the box was empty, and then we'll take home 12 for sure. And this is 19. So we see that we are actually better than any of a pair of boxes that we could open by being adaptive depending on what we found in the first box. So our question for today will be, how much are we losing if we decide to be non-adaptive as opposed to being adaptive, meaning that we make our choices depending on what we find in earlier boxes. This is what is called the adaptivity gap. The adaptivity gap is the following. Take the best policy let's call this pi star, and what's the expected reward that you're getting if you start in a state and go for t steps, and we now divide this by the best non-adaptive policy. So everything is the same except for that we constrain the policy to be non-adaptive. And what do we know? If we look back at our example, then we see that our adaptivity gap here is at least 19 over 18, because the best non-adaptive policy will give us 18. This is some adaptive policy which will give us 19. Maybe there are even better adaptive policies. And why do we care about the adaptivity gap? Well, Stating such an adaptive policy might really be difficult in the sense that any description might be huge, because it is actually would have to represent this decision tree. Meaning that this now states, okay, open this box, then depending on what you find, do this or do that, and this might be huge. Whereas stating such a non-adaptive policy, this is just stating which boxes you should open. Still, finding the best non-adaptive policy might still be difficult, because also finding just a subset of boxes, this is not exactly easy. Like if you think about the knapsack problem, there just finding what you want to pack inside your knapsack, this is also a difficult problem. Nonetheless, what we're doing today is we will be devising a polynomial time algorithm which computes a non-adaptive policy. And this non-adaptive policy is within a constant factor of the best adaptive policy. So we are at the same time able to compute a good policy, which is easy to state, and also we're giving a constructive proof which actually bounds this adaptivity gap. In order now to devise our algorithm, which will compute this non-adaptive policy eventually, we will devise an LP relaxation. This LP relaxation has the property that it bounds for us the value or the expected reward of any policy. So any policy corresponds to a feasible solution of this LP, and then we can solve this LP in polynomial time, and from the solution that we derive, we can then obtain a non-adaptive policy which is within a constant factor of the objective function value of our LP solution. And how do we do this? Let's have a closer look at the probabilities that are involved in any policy. Namely, we can now write down the probabilities with which it opens a certain box, and also we can write down the probability with which it takes home a certain prize. So for any policy pi, we now write the following random variables, which are yi is 1 if box I is opened and it is 0 otherwise. And we'll also write z subscript I comma v, and this is 1 if box I contains a prize of z and this prize is selected. And we'll say that xiv is 0 otherwise. And now we can also define small yi as the expectation of capital Yi, which is nothing but the probability that capital Yi is 1, and also small z subscript iv as the expectation of capital ziv, which is nothing but the probability that ziv is 1. This first definition, I think, is clear. This is just or also what does the yi mean? This is nothing but the probability that box I is opened, the a priori probability before having opened any boxes. But this ZIV is a little more complicated because we now have the statement that we, on the one hand, see this price of V inside there and that this price is selected. So maybe let's once again consider our policy that we saw earlier, which opened the boxes adaptively. There, the first box is always opened. Which means that small yi will be 1. And the other two boxes, recall that we open them if and only if the first box, or depending on what we find in the first box, and both happens with probability half. So the other boxes are opened with probability half. This now, of course, depends on what we see inside the first box. So we would have that y2 and y3 are equal to a half each. Of course, there is some correlation here, namely that if y2 is, so capital Y2 is 1, then capital Y3 is 0, and vice versa. This is not reflected at all when I'm now stating here this regarding the probabilities. Now let's talk about these small ZIV. What would Z124 be? Well, what does this mean? This means that we are opening box 1 and we're taking home, that we are taking home the price of 24 from box 1. So when did this happen? This happens if, and maybe let me go back to the example. When did we take home the price from the first box? So the first box we have here, this contains 24 with probability half. So when do we take home this 24? Well, we take it home whenever we find a half, whenever we find the 24 inside this box, but then the second box that we open actually turns out to be empty. So this means that the value of x124 is actually a half times 2/3, because this is exactly the probability that we're taking home the 24. And you can also see the other probabilities here. So this is why we are getting now that this x124 is, as I was saying, a half times a third, times 2/3. So this will be a third. Then we also have this Z3,12. What's the probability that we're taking home the 12 from the third box? This is exactly a half, because this was happening when the 24 box turned out to be empty, and then we were going to the 12 box. And we can also take home a price of 30 from the second box. When does this happen? This happens when we find the 24 in the first box and the 30 in the second box. So this is happening with probability a sixth. What we'll now do is we will now write down some constraints that these y and z have to fulfill for any policy. So far we're talking about an arbitrary policy which may be adaptive, and for any policy there are these y and z values, and these y and z values, they cannot be arbitrary. For example, they are constrained by the fact that we may take home at most one prize, and that we may open at most k boxes. So, what does this look like? Well, what is the expected reward of our policy? This we can now also write in terms of the z, capital Z variables. Namely, when does this happen? This happens if z subscript I, v is 1, then we're taking home the respective v. And for this now we have to take the sum over all possible I and v, and this way we can just express the prize that we're taking home, and the expectation of this is the expected reward of our policy. And by linearity of expectation, we can of course write this as the sum of the v times the expectation of the ziv, which is nothing but the sum of the v times small ziv, because the small ziv are the expectations of the capital ziv. What else do we have? We have that the sum of the yi will have to be at most k. So what does this tell us? This tells us that the sum of the small yi, and so by the way this has to always hold, so with probability 1. And what does this mean for the small yi that we can open at most k boxes? Well, the sum of the small yi is nothing but the sum of the expected capital yi, which is nothing but the expected sum of the capital yi. And because point-wise this is at most k, we can say, okay, this will also have to be at most k. And also we may take home at most one prize, which means that the sum of the ziv, capital Ziv, will be at most 1, also with probability 1. And this means that the sum of the small ziv, which is the sum of the respective expectations, this will have to be at most 1. We have one further thing, namely that for ziv being equal to 1, it is necessary that, well, the one thing is, of course, that yi is equal to 1, namely that we open the box. And the other thing that has to hold is that the box contains a prize The other thing that has to hold is, of course, that xi is equal to v, so the box contains a price of v. What does this mean? This means that that small ziv, which is nothing but the expectation of capital ziv, or in other words the probability that ziv is equal to 1, This is at most the probability that yi is equal to 1 and xi is equal to v. Now what is happening here? The probability that yi is equal to 1 and the event that yi is equal to 1 and the event that xi is equal to v, those have to be independent, because when we are opening box I, we don't know what's inside the box. No policy knows this, because it is still a policy, so those are independent events. We can instead write down this as the product of these probabilities, and now what this is that this is small yi times, and for this we earlier introduced the notation FIV. Good. So, where are we now? We've now figured out a couple of properties of the yi and zi, well, variables, so to say, which were the respective probabilities, and any policy we can now describe like this. Its expected reward is exactly given by this term, and also the yi have to fulfill this constraint, the ziv have to fulfill this constraint, and also the ziv have to fulfill this constraint. And what we now do is we write down this as a linear program, because all of this is actually linear. And then what we will do is we will simply solve this program optimally. Unfortunately, this does not necessarily correspond to a feasible policy, but we will turn it into a policy. Before we get there, let's first once again write down what we now find out. So our LP relaxation is maximize the sum of all v times ziv, subject to the constraints that the sum of the yi is at most k, subject to that the sum of the ziv is at most 1, that each ziv is at most fiv times yi. This has to hold for all I and v, and that ziv is at least 0, and actually also yi has to be at least 0 for all I and v. And we now have that the expected reward of any policy is upper bounded by the optimal solution of this LP. And the proof just follows by the observation that we made before. Namely, that our policies have to fulfill these inequalities. As a matter of fact, not every policy corresponds, or not every feasible LP solution corresponds to a policy. This is what I said earlier. Namely, what could happen? The following could happen. Maybe it's instructive to see this. I now want to just consider the example that we have two boxes. First one contains a price of 2 with probability a half, and it is 0 otherwise. And the second one contains a price of 1 with probability a half, and it is 0 otherwise. And now I allow you even to open both boxes. Now there's not much discussion about what the optimal policy is, just open both boxes. But what's the expected reward that you're getting? Well, with probability a half, you take this 2 home, and with probability a quarter, you take this 1 home, and with probability a quarter, both of the boxes are empty, so you're taking home nothing. But if we now look back at this linear program actually doesn't take into consideration any correlations. And what we could do here is we could set actually the yi to 1 for both boxes. Okay, that's exactly what we're doing. But the ziv we could also set to a half for both boxes when they are not empty. Then also these constraints are fulfilled. So it is a feasible LP solution to set y1 and y2 to 1 and z1, 2 and z2, 1 equal to a half each. Then the value is equal to 2 times z12 plus 1 times z21, so this will be 1.5. But the optimal policies value is how much? It is a half times 2 plus a half times 1 plus a quarter times 1. So this is 1.25. So this is why this LP is actually a relaxation. Not every LP solution corresponds to a policy. Why is this? Because the LP doesn't actually encode that sometimes it may happen that we see this price of 2 and this price of 1 or at the same time. The LP is just saying, okay, well, you may take the 2 with only probability a half and you may take the 1 with only probability a half. But that the fact that it may sometimes happen that both boxes are non-empty and still we may take only one of the prizes home, this is not encoded in this LP. But that's not too bad still, because what we can do now is we can still solve this LP and from a solution to this LP derive a non-adaptive policy, which is whose expected reward we can bound in terms of the objective function value of our LP solution. Now what we want to do is we want to derive from an LP solution, so we can now solve the LP, and from a solution we can then derive a policy. And namely, we will derive a non-adaptive policy. What will this look like? Well, what we will do is we will solve the LP and get an optimal solution x star, comma z star. As we saw, this does not necessarily correspond to any policy. And now what we'll do is, for I from 1 to n, as long as less than k boxes have been opened, what we'll do is we will open box I with probability yi star over 4. And then eventually we'll of course keep the highest price. This policy is clearly non-adaptive because it just goes through the boxes. Well, we now say that we open a random subset of the boxes just because we're doing this for analysis purposes. This definitely shows also that the best non-adaptive policy, which opens a deterministic set of boxes, will be no worse than this. But this is just a randomized algorithm which devises a non-adaptive policy. The point is, it doesn't actually matter what we find inside the boxes. So this is something that we can do beforehand, just going through this and then deciding, and then this actually decides which boxes we should be opening. How do we analyze this? Well, we analyze this by now considering a slightly different policy, which does something that we actually don't have to do, namely, it commits to keeping a box when it sees its contents. So what we'll do here is we'll replace this keep the highest price and we'll move inside this for loop a decision whether we keep the current price or whether we keep opening boxes. So this will be our immediate decision policy. And the first step is still the same. And now we also do this iteration over the boxes. And now things become different. Well, this is still the same. We open the box I with probability yi star over 4. But what we now do is we observe the price and we select this price with probability z subscript I comma v star divided by fiv times yi star. This will make sense in a bit. And then we just select it with this probability without looking actually at any further boxes. So technically speaking, this is not non-adaptive anymore because, well, this now depends on what we see inside the box. We decide whether we keep opening boxes or not. But the point is, compared to this non-adaptive policy, which is the one that we actually want to analyze, the expected reward can only be smaller, because here we're actually tying our hands because we make these immediate decisions. And by the way, if we never choose to select this any prize, then we're actually going home with no prize. This is something that we're doing just for analysis purposes. And what we will show now is the following. We will be showing that the immediate decision policy has an expected reward of at least 1/8 times the sum of the V times CIV star. And what does this tell us? This tells us in particular that the adaptivity gap is at most 8, because this is the expected reward, or this is an upper bound of the expected reward for any policy, and now we get this much, so only a factor of 1/8 less, for our policy, for which we were arguing that this policy that we have here, this immediate decision policy, can only get a smaller reward than this non-adaptive policy that we were devising. Good. So all we want to do is we want to now prove this theorem, which fortunately isn't actually too difficult. So let's do this. We will now devise random variables that we used also before. We'll say yi is equal to 1 if box I is opened by now our policy that we're understanding here. It is 0 otherwise. And we'll have ZIV being 1 if box I is opened, contains V, and is selected. And we'll set this to 0 otherwise. Good. Now, of course, what is it that we want to bound? We want to bound the sum, the expectation of the sum of the I, V, V times ZIV. And how do we do this? Well, we want to understand what are these ZIV. When does our policy open a box? When does it happen in our policy that it opens box I, the box contains prize V, and this box is selected? Well, let's maybe go back to how we do these things here. Suppose that our for loop here reaches actually iteration I. Then we open the box with a certain probability, and then we see the prize inside, and then we select it with a certain probability. So if this thing here happens, then ZIV will be 1, otherwise it will be 0. And what was important for this? Well, a couple of things have to happen, namely that the for loop reaches this iteration at all, so that we didn't select anything before. Then we'll have to open the box, and then this selection also has to happen. And we can now write this as follows. If we let fi be the event that the for loop reaches iteration I, then what is the probability that ziv will be equal to 1? Once again, conditional on fi happening. Well, then what will have to happen is that first of all we have to open the box, which happens with probability yi star over 4. Then this box has to contain a price of v, which happens with probability fiv. And then we'll have to actually select this box, which happens with probability fiv times yi star, ziv over fiv times yi star. This is exactly how we define it in our policy. What's the probability that we actually select what we find there? And now you see why we're using exactly this probability. Because now things nicely cancel. Now we're getting a probability of ziv star over 4 that we're actually taking home this box right now. So we will then show that the probability that fi takes place is at least a half. And this then tells us that the probability that ziv is equal to 1 is actually at least a half times small ziv star divided by 4. So this will be ziv star over 8. And this means that the expectation of the v times ziv will be the sum of the ziv the sum of the v times the expectation of the ziv, that this will be at least the sum of the v times ziv star over 8. And this is exactly what we claim. So all we have to show is that this bound here holds. That the for loop reaches iteration I with probability at least a half. And how do we do that? Well, when does it happen that the for loop does not reach iteration I? Well, maybe let's go back to how we defined these things. When do we not reach iteration I? Well, two things can happen. Either there have been too many boxes have been opened. There are already k boxes which have been opened before, or one of the boxes has been selected, and then we're not looking at any further boxes. So this means that in our notation here, it might happen that we've opened too many boxes, which means that the yi prime for I prime smaller than I is at least k, or that we've already decided to take home a prize, which means that the sum over all I prime smaller than I, taking the sum over all v, we have that these z I prime comma v are at least 1. And this now means that we want to bound the probability that either of these events, that one of the two events happens, and for this we will use the so-called union bound, which is just a tool from probability theory, which says that for any not necessarily disjoint events, E1, E2, and so on, we'll have that the probability that the union takes place, this is at most the probability of the individual probabilities, the sum of the individual probabilities. How do you prove this? This is actually just by, you can prove, for example, by induction, and then you see, okay, what we're now ignoring is actually the intersections, and this is why we have only an upper bound here. If these were disjoint events, then we would have this with equality, but since we are not saying that they have to be disjoint, we only have this inequality here. So this tells us now that the probability that Fi is not happening, so the complement of Fi, this is exactly the probability that the sum of the yi prime is at least k, or the probability or the event that these zi prime are at least 1, and this we can upper bound by just the sum of these probabilities. And now the only thing that we'll have to do is bounding these probabilities. And how do we do that? That we can do using Markov's inequality, which you may have seen before, or maybe not, doesn't matter, it's super easy. Which says that for any non-negative random variable x, and any alpha, which are strictly greater than 0, we have that the probability that x is at least alpha is at most the expectation of x divided by alpha. So this gives you a pretty weak bound. Usually this is far too weak, but this is enough for our purposes now. The probability that you're, for example, much higher than the expectation. This is what you can bound this way. Namely, what does this give us in our in our case here? We have that the expected sum of the yi prime is how much? Well, this is, what's the probability that we open box I prime? It is at most yi prime star over 4. Maybe it is even less, because this doesn't take into consideration that the for loop might have stopped earlier, some things like this. And for this we know from the LP constraint, because what we were starting from an LP solution, that this will be at most k over 4. So this tells us that the probability that this sum here is at least k, this will be at most k over 4 divided by k, so this will be at most a quarter. And similarly, we also get this for this term. So the probability that we've already taken home a prize. What's the probability that we take home a prize? Well, what was the expectation of such a zi prime v? Well, I think we've already derived this. Yes. Okay, maybe this is even too strong as a bound. We can definitely use this bound here as an upper bound, so certainly the probability will be no more than ziv star over 4. So we will have here that this is ziv star, and because we have over 4, and because we have a feasible LP solution, this will be at most 1 over 4, so the probability that this sum here is at least 1, this will be at most a quarter divided by 1 by Markov's inequality, so this will be at most a quarter. And now putting these things together, we've now seen that this is only at most a quarter, this is at most a quarter, so we get that the probability that fi bar is taking place is at most a quarter plus a quarter, so a half, and this means that the probability that fi is taking place is of course 1 minus the probability that fi bar is taking place. This will be at least a half, and this is exactly what we claimed. We namely claimed that the probability that the for loop reaches iteration I is at least a half. And this now concludes our proof. Good. So these calculations are maybe not super inspiring. The idea is actually pretty simple, namely that we don't use zi or zi star or yi star as the probabilities, but a scaled down version of this, which leaves us just this slack that with a pretty good probability, we won't be opening too many boxes. We won't be taking home a prize early. So if you look at this carefully, you will realize that even now, with probability a half, we are not, or with probability how much, we are not taking home any prize at all. I think it's even 3/4 now that I'm looking at this carefully. With a pretty high probability, we're not taking home any prize. Good. This is where you see, okay, there's a lot of slack in here where you could actually improve this, but this is not the point. If you want to improve this, sure, there are much better calculations than this, but the general techniques work just as I showed them now. What you'll do is you'll relax this as an LP. Maybe you might want to introduce further constraints if this is any reasonable, but even without further constraints, you are able now to derive a policy which is a very simple policy, and you can bound its expected reward in terms of the reward of any policy, because you can bound it in terms of the optimal LP solution. And this, importantly, works without actually being able to, for example, compute an optimal policy. Computing an optimal policy would be super difficult here. This just because even describing the optimal policy is, as I was saying it earlier, very difficult. Because this now depends on, okay, I now saw this and those boxes have been opened. How would I continue? And I think in this slide, it is actually pretty interesting how simple this Pandora's box policy is, where we just have an index for each box and we just open boxes by decreasing index up to a certain point, but we don't have to adapt this depending on what we saw or something like this. And as you see, it only matters whether what kind of constraints you have, whether you have this soft constraint that you kind of want to just keep your costs small, or if you have this hard constraint that you may open only 2 boxes. By the way, you can easily generalize this to the setting where each of the boxes has a cost, but the amount of cost, the sum of the costs that you're allowed to spend is bounded by k. So in this case, the cost of opening a box would be 1, and you have a budget of k, but you could now also have a different cost that you're allowed per box. This wouldn't actually make a huge difference. The calculations would change slightly, but not drastically. Good. So, this concludes today's lecture. Once again, we've seen the integrality gap, we've seen pretty fancy boxes, and we've seen a very simple technique, namely relaxing the problem of finding an optimal policy as a linear program. And importantly, the offline optimal solution, this has nothing to do with the offline optimal solution. The offline optimal solution might only open 1 box where it knows where to find the highest price, but this is not a feasible LP solution, because when we were showing that feasible LP solutions are feasible policies are feasible LP solutions, we at one point said, okay, the policy actually doesn't know what's inside the box before it opens it. Good. Yes, this is it for today. Please do let me know if you have any questions, and I hope we see each other next time. In the meantime, stay safe, have a great day, bye.